All right, so this is part 2. We talked a little bit about what isolated user mode was in general. Now, tell us who you are and what you do.
So my name's Logan Gabriel. I'm a senior Windows security engineer. I've been at Microsoft for 3.5, coming up on 4 years.
Fantastic.
And I got the privilege and the luxury of being the lead pen tester for this awesome virtual secure mode, virtualization-based security platform.
That's cool. So what's a pen tester?
So a pen tester is someone who comes in from a attacker mindset and tries to attack a given set of security promises and tries to undermine them, tries to see where are real attackers going to go, where's the real attack community going to go, where are the exploits going to be, what areas do we need to focus on, what do we need to harden.
So you're like a white hat hacker.
Exactly.
Nice. That's cool. So why don't we do this? Why don't we start off with where we left off, and then we'll talk a little bit about how this is implemented and what processes can actually use this.
Okay.
So let's go to the diagram again.
Okay. So we've redrawn the diagram that Dave put up earlier.
And so the left hand is normal mode, the right hand is secure mode, and then the top is the kernel and the bottom is the user space and the hypervisor lives underneath. Is that correct?
Exactly.
Fantastic. So I asked beforehand, can a developer just use this yet? And the answer was no. What does use this right now and why?
So right now, the main thing that uses this is a process called LSA ISO. LSA ISO is what keeps the domain level security credentials, namely the NTLM hash, secure and safe and isolated. And this is a good mitigation for the pass the hash attack.
I see. So describe the pass the hash attack. What is that?
I think that attack is a little bit out of scope. It's very complicated to get into. It's a little bit nuanced to get into. There's lots of research out on the pass the hash attack. It's probably not the best thing to dive into from the sake of you of explaining how the process model works, how the architecture works.
In essence, it's a secret that we don't want anyone to get.
Right. It's a secret, and if you can exfiltrate it from a machine, you can use it from another machine to laterally traverse your way across a network.
Okay.
At a very high level.
And so in the secure mode, how is that being protected using what we've learned just before?
So the key golden secret, the thing everyone wants to steal, is this NTLM hash. That's the object that's replayable. That NTLM hash lives over here in secure world in this process that we call LSA ISO. All the cryptographic operations, all the challenge response operations, all interaction with that secret is explicitly contained inside this secure mode.
And so why is that a good thing?
Because the secret can't be stolen off the machine.
I see.
Or it would be very difficult to steal the secret off of the machine.
So now the kernel doesn't even have access to that particular program.
Right. So if you have a device driver attack, if you have an exploit that gets code execution over here in the normal world kernel, that, through lots of pen testing, cannot get access to these secrets, or is very hard to get access to these secrets. We fixed all the ways that I found to do it.
So how do you go about even starting to test that or pen test that?
We wrote a custom driver. That's why this was one of the most fun projects I worked on. We wrote a custom attack driver that lived in the normal world kernel and exercised all the options that it had available, poked at the memory manager, rewrote whole pages of the operating system function, like at attack time. It was a really fun project.
So you, in essence, just went into the candy store and started knocking the shelves over, is what you were doing with that.
It was more fun than that.
And so did you find that this particular driver in normal mode could seriously undermine certain things in normal user mode?
At first, we had a couple of good bugs. All of those were fixed. When all the pieces started coming together, we found it was very difficult to attack any of the secrets in here through any of the runtime operating system mechanisms.
So this is pretty cool. So talk about the future, because it feels like you said there was only a couple of processes that are running in secure mode, and it seems like they're really important processes that hold the really important secrets. Is there a way to just push all of the secrets over to secure mode, or is that something in the future? Where do you see this going?
I think that's kind of a future thing. This is a platform and an architecture to demonstrate these are the kinds of possible things that we can solve. It took some rewriting to make LSA ISO. We call it Credential Guardian, by the way. It took some rewriting to make Credential Guardian work in this model. It takes rethinking about the problem space. This is a very hardened container. Not all the things that normal programmers are used to having accessible function by default in these containers. You have to have a very security-oriented mindset when coming to it. So it's difficult to speculate about, what the add-on options will be in the future.
Okay.
But this is an architecture that I think creates lots of potential.
So let's talk about a process working in the secure mode. What does the process have access to? Because it's not actually accessing a real kernel, it's accessing a secure kernel, which is kind of like a shim.
It's accessing a real kernel through proxy layers.
Got it.
And the proxy layers marshal all the parameters that the application, the secure application, tries to get from the normal kernel, and by default sanitizes responses that come back from the normal kernel, because you don't want the normal kernel to be able to attack or mislead what this is, because the traditional trust model we've been working with is applications in user mode trust the data that comes from the kernel.
That's interesting. You talked about, because this is something we didn't talk about beforehand, sanitizing data that comes from the kernel. That's something the secure kernel does.
Yes.
What does that mean?
It means that for a given set of system calls, we identified, and I won't go into the specifics with it, but we identified a number of parameters, a number of options, a number of data structures or other things that could mislead an application. And we do validation, we do verification, we throw out some options, we do lots of sanitizing, scrubbing parameters out, scrubbing memory buffers after they've been used. Lots of security hardening has gone into this. We had a whole review project for over a month to look at all the system call attack surface and what are all the things that you can do to abuse system calls and what do we need to scrub and protect.
That's really neat. So you're saying that this kernel that marshals stuff over not only acts as sort of a gateway between the actual kernel, but it actually does some policing on the way back.
I think about it like a partial trust broker.
I see.
Which is a concept that's more familiar in like user mode code, COM code, those kinds of interfaces, but that's a term that people will recognize and will resonate with them.
So, and I know this isn't possible yet, but if someone were to write a process in secure mode, what limitations are there, if you can talk about that? Or where do you see these kind of processes in the future? What other processes do you think we could add to the secure mode?
Again, that's kind of speculation. Any process or any kind of process that you would like to have a strong guarantee that it has a secret and it can keep the secret. So any kind of derived data, if it's going to do a encrypt decrypt operation, if it's going to do a signature operation, any kind of operation where the true secret is kept isolated and the exported data is only derived.
I see. So you said there was, how many processes are running it now? You said there was one process that saves the NTLM hash, is that what you call it?
Right.
Is there any other process running in there currently?
So this is what's going to ship in the client SKU for Windows 10.
That's awesome. Okay, so let's talk a little bit about, there's any other things that you'd like to talk about with respect to server, because we've been talking a lot about the client mode. Tell us about server and secure mode.
So in the server mode, we have another process, another trustlet called VTPM, which is going to act like a isolated TPM, where if you look at the model where a normal TPM works, the normal TPM hardware, TPM, has a endorsement key and a set of private keys that are very hardened to physical attack. We have the same kind of model with the VTPM trustlet, but The keys that the VTPM holds are contained inside the secure buffer, and it only releases or signs derived secrets out.
So you said a couple of acronyms there, TPM and VTPM. What are those?
Okay, so TPM is a trusted platform module. It's a piece of silicon that comes on a given computer logic board. It's hardened against physical attack. It is a hardware device that keeps secrets.
I see. So here, I had this, because I had to set we have a card at Microsoft that has a chip on it.
Right.
I had to stick it into my machine and do something TPM-ish.
Right.
What was that?
So that was called a virtual smart card enrollment process. And that's a process where you enroll the physical identity of your smart card with your TPM, and the TPM keeps that secret, and the TPM is able to sign requests on behalf of that smart card.
I see.
These are the mechanisms that we're pushing and creating with virtual TPM by having a virtual TPM trustlet.
I see. So now instead of having to have, and you might still have a TPM chip, you're able to use sort of a virtual TPM in software in secure mode.
Right.
I see.
And we do that so you can get the same quality security guarantees for virtual machines as if they're talking to virtual TPMs.
Oh, I
But they're
see.
isolated and unique from each other, so you don't have problems of one virtual machine resets the TPM and it messes up the TPM state of another virtual machine.
I see. So you might have several VMs running on this huge machine that has virtual TPMs to verify access
Correct.
for certain people.
Or you might want to migrate the VMs to another machine.
I see. So now let's get to the last thing. You mentioned something called a trustlet.
Right.
And is that a process running in secure mode?
Yes, so a trustlet is just what we call processes running in secure mode.
Awesome. We talked about these trustlets. What does that have to do? Because when I first came to Microsoft, because I'm still new, they made me turn on this thing called BitLocker.
Right.
What does that have to do with all of this?
So BitLocker is a physical drive encryption solution. The really exciting thing that we're getting with virtual machines, with VTPM, and virtual machine migration is the ability to protect data at rest inside the cloud for virtual machines. So you want to migrate a virtual machine from one cloud provider to another cloud provider, you can keep all the data protected across the whole pipeline.
Interesting. And so, in essence, what we're able to do with secure mode is lift some of the security features out of hardware into software so that now we can migrate virtual machines that have BitLocker, that have TPM stuff in
Exactly. That's why this is a platform. That's why this is a really fun project to work on and a really exciting domain space to work through, because it is going to enable all of these future scenarios with really hardened security guarantees around them.
Now that we've talked a little bit about lifting these hardware things, is there any way to get people to not tamper with these things? Say they just run rogue and start wiping memory everywhere. So
one of the really exciting things that we were able to do with this was we were able to bind in secure mode. We were able to bind, let's say, okay, here's a common attack scenario. You just want to turn a security feature off. Okay, we've seen this attack a lot. We have an awesome new mitigation, it works really well. An attacker gets in, an attacker just says, turn it off. Okay, you take that approach inside of a machine with VSM enabled, and all the keys are gone. So you can't just turn the functionality off, all the keys have been gone. You can't steal secrets from the virtual TPMs, from the LSA ISO, because all the keys that were used to protect those secrets have been destroyed when the functionality is turned off.
I see. So now if there's a functionality, so describe it a little more, because you used a couple of acronyms that I haven't heard. VSM, I think, was one of them?
So VSM, virtual secure mode.
There you go. So secure mode. So if you go in there and shut that off, it destroys the keys as well.
Right.
That's cool.
Right. Right, and we did a lot of pen testing around that to make sure that that worked right. That was one of the attack scenarios that we identified early, and that was one of the great value adds that security engineering was able to provide, was identifying that scenario, and now I feel like we have a really good end-to-end solution there.
That's awesome. So we talked about a couple of trustlets, one for client, one for server. Are there any other trustlets that have been built?
Trustlets, no. One of the other anti-tampering features that we have is something called HVCI, and that's something that I'm really excited about and really impressed with too. HVCI is a code integrity in the kernel that can be enabled to protect large parts of the system. It leverages the SLAT mechanisms. It basically works like code integrity, except you can't manipulate the write execute bits because they're controlled by the hypervisor and they're controlled by the SLAT. So that was actually one of the large barriers in our pen testing effort, was the pen testing driver that we wrote. It had a bunch of mechanisms that used a technology called detours, which is something you can look at for MSDN,
Okay.
to rewrite functions in the kernel, to manipulate pieces of the kernel. It was one of the things that we were interfering with the system call hijacking, the system call filtering with.
I see.
HVCI blocks all of that. And it was really impressive to see all of that work, because you flip HVCI on, you try and redirect a function, and it stops.
You talked about HVCI. Is that something that's happening in a trustlet, or what is that?
So HVCI is running in secure kernel, most of it, and there are small pieces that control the SLAT and the memory protection pages inside of the hypervisor. But the code integrity part of HVCI is checked in secure kernel.
I see. So for example, if you're trying to load up some code that's not, you don't want it to be executed, the secure kernel will tell you through SLAT, that's read-only.
Right.
And if you try to redirect the function call, it's going to say, nope, you can't do that.
Right.
That's interesting.
Right.
Okay.
And it works beautifully, and at first I thought I had a bug in my driver when it was turned on and it wasn't working. And
It wasn't. You were trying to access a bad thing.
right.
And the secure kernel through HVCI was saying, you can't rewrite the pointer to that function call.
Right.
That's really
Beautiful.
interesting. And so we talked about trustlets, but then we sort of lifted stuff into the secure kernel that's not necessarily a trustlet. Is there anything else in the secure kernel that's running that we should know about?
All the crypto code is running in the secure kernel, and we've paid a lot of attention to how the crypto is going to work, how to attack pieces of the crypto, how to mitigate attacks against the crypto. We have completely different entropy pools. We have completely different random number mechanisms. We have all of that stuff is done in secure kernel to protect the secrets, the base level secrets that anything in secure user mode derives keys from.
That is interesting. And because I don't know if people realize, but secure numbers in computers aren't really secure numbers. They're just
Random numbers are hard to
that's what I
come
mean,
by.
random. They're just like for example, in .NET, if you put the same seed in, it'll give you a random number, and it'll give you the next random number. But if you give it the same seed every time, you'll get the same sequence of numbers.
Exactly.
And in cryptography, that's a problem.
Right, right. There's a great XKCD comment about it. The dice one. Hard-coded, 2. Guaranteed to be random, chosen by dice roll.
So that's really cool, because you talked about trustlets, and then you talked about HVCI working in the kernel mode, and now you're saying that the secure kernel will also, like for example in .NET, most people don't realize when you do a random number and you give it the same seed, the sequence is exactly the same every time. And so if you're generating random numbers to do cryptography, if you can find what the sequence is, that's a problem. And you're saying now that's all happening in the secure kernel.
Yes, exactly.
That's awesome. That's awesome. Is there any other sort of goodies in the secure kernel that you'd like to talk about?
It just makes me really excited.
That's awesome. It feels, to me, it feels more secure because
It's a paradigm shift. This is the foundation framework for a paradigm shift in how data is kept secure on modern hardware with modern operating systems.
and it's also upside down from the notion that everything that the kernel gives you is gospel, because sometimes it can get you.
Yep.
That's awesome. Well, thanks so much for spending some time with us, bud.
Thank you too.